Video, I'm going to be reviewing the IV Delta Surface notebook provided by Amber Data and Genesis Volatility. Within this notebook, we're going to be looking at two specific endpoints, such as the live Deribit fixed delta surface endpoint and the hourly fixed delta surface endpoint. Each of these endpoints serve unique purposes, one of which would be retrieving live data in real time and historical data. The purpose of this notebook is to give you a more general understanding of how to use these specific endpoints for your own data analysis, for trading in crypto markets with using Bitcoin and Ethereum. So throughout this notebook, you can notice there's a lot of stuff going on, and it's quite a long notebook if you look at my scroll wheel on the right, but we're going to go through into the main details and explain which components are important and how you can use each of the plots I'm going to mention. So without further ado, at the start of the notebook, we have all of our basic imports that will be provided in the notebook. Additionally, this notebook will be accessible on our GitHub as well, and you'll be able to find that in the description of the video. Within this, the first thing you want to do right here is plug in your gVault API key. This will be user specific, so this will be something that you will have access to, and you're going to plug this in and copy and paste it as a string to run these queries. Now, once you run this cell, you can move on to the next cell over here. Now, this cell is basically running the GraphQL query from our database to pull this live Deribit fixed delta surface endpoint. From this endpoint, we'll parse the results and put it into JSON format, and then we'll normalize the results into a pandas data frame, which we can then use to analyze the data and then plot. The next additional cell is a very similar, it's set up in a very similar manner. In this case, it's using the hourly fixed delta surface endpoint. So this is historical. As you may notice, I'm plugging in yesterday's date because all the data points within inside of this endpoint are specific to the end of day yesterday. So if you want to get today's latest queries, that'll be the previous endpoint versus yesterday's will be right here. So anytime you run this, it will always pull up to yesterday, and you can predefine which currency you want to run it on and your start date up until yesterday, or another predefined variable or time frame if you like as well. Similar to the other endpoint, we'll also normalize the JSON into a pandas data frame under a historical data frame called dfhist, and we'll use that alias further down with the rest of our data. And one thing you might notice as well is I have different markdown cells mentioning each of the components for each of the cells regarding the main takeaways from each of them. So the second step after we pull all of our data in and query it from gVault, we are going to melt the data frame. And this basically turns strings of texts from the column names into actual usable integers. Now in this case, we're looking at IV delta surfaces. We're going to want to extract the string values and turn them into integers. So in this case right here, you can see we have 5 turning into an integer of 5, 15, integer of 15, and the string of 25 to 25 and 35 to 35, just so we can use those values for plotting purposes. And then we do some other matching right here as well to map them out and also get some more cleaner and neat details that we can use to plot. So that's the gist of this function. You don't have to adjust any of this. All of this should be pretty straightforward and just should make your life a little bit easier when trying to parse this data. So now we're going to go on to the plotting functions portion of this. Let me delete this cell real quick. That's not needed. So on the plotting functions portion, as you may notice, I will have a lot of different functions right here predefined in the same notebook instead of being imported from an additional script. Now, each of these plots have different purposes. I'm going to dive through each of the plots down below. But this is essentially the whole function sheet of code for you to edit it how you like, see how I'm computing different plots and so forth. But yet again, since they are just plots, I'm not necessarily manipulating the data in any specific manner. I'm just making them visually friendly for you, the user, to then use and analyze data with. So I'm going to go through the bottom of this. Oh, whoops. I'm going to go through all the way down here after I get through those plots. And this is where I can start viewing all of the plotted data. So first and foremost, we're going to be looking at the delta plot, which is the implied volatility over time for a specific option type and delta. As you may notice as well, similar to what I mentioned earlier, I add additional markdowns for each relevant plot to make your life a little bit easier when trying to understand what the context of the plot is doing and how you can use it to potentially predict future price movements on a underlying asset, which will be, in this case, Bitcoin or Ethereum. So instead of writing out all that code over and over again that you saw at the top, that like 300, like the 350 lines of code, rather, you can have it all right here. So for you as the user, you can go, okay, let's look at for example, a call option, and we're going to select a delta of 5. And we just want to look at a basic delta plot with the historical data frame of the option type, which is call, and the delta, which is 5. And we can plot this out right here. And as you can see, we have a perfectly clean time series of this of this 5 delta call option that we can see over time. And one thing I must mention right here, you might notice this and go, okay, well, sure, we're looking at 5 delta call options, but what do these numbers mean? What makes them different from each and one another? Well, notice there's a 7, a 30, a 60, a 90, and a 180. That is the expiration, or that is the maturity of the options contract. So when we look at 7, that is the 7-day 5 delta call. 30, that's a 30-day 5 delta call. 60, and so forth. It continues on. So all those numbers you see right there are interpolated from will be an interpolated fixed expiration or maturity on a 7, 30, 60, 90, or 180-day basis. But this is the gist of this plot. And then you can read more descriptions on it if you like to answer your questions about it and potentially use it for your own analysis. Looking at this next plot, we're going to be talking about the delta risk reward plot, which is the implied volatility risk reversal over time for a specific delta. So similar to what we had before, you can specifically mention if you want to call or put. Instead of specifically mentioning a call or put, you can choose whether you want to do a put minus a call or a call minus a put, but you can still pre-select the delta just like the one before. That's what I meant to mention. So by subtracting the call from the put, we're essentially normalizing the skew from puts against calls and just plotting the real value of the implied volatility against each end. So for instance, if you have put minus call and the value on here is positive, we would argue that the put implied volatility is therefore higher than the call implied volatility, meaning that there is more skew to the put side of the options chain for this 5 delta put strike. And you can use this how you like as well, but that is a very brief description of what's going on here. And this will be a common trend. We are going to be using this plot a few more times down the line. Now, speaking of which, here is quite literally the same thing as not this one, but the one before it. So right when we're looking here, we can see, we're looking at a call option of a 5 delta. Okay, cool, unique, right? But let's say we wanted to normalize that call option and remove any implied volatility aspect to it alone. So we're essentially looking at the same data as we were 2 cells ago, but instead of the same data, we're dividing whatever number or whatever the results of that data is by the at the money 30 implied volatility. And you can choose between at the money 7, 30, 60, 90, or 180, similar to the expirations that we have defined on the side as well. And this essentially flattens the majority of the data so you can get a more direct comparison with respect to implied volatility rather than looking at the data naked and on its own. So this is a very useful way to analyze that on your own. Now, same thing goes here. So rather than the previous one where we look at the specific call option or put option with a specific delta in respect to implied volatility, we're going to be looking at puts minus calls in respect to implied volatility to flatten the curve and also get a taste of skew. And this can also be used for a variety of manners for analyzing data, and you can use it how you like, but it's right here. Okay, to move on a more simple note regarding plots, this one is just the at the money implied volatility over time. So there's nothing special here. It's only a time series of at the money 7, 30, 60, 90, and 180 on a time series basis. You can see there's no term structure here, and everything is very streamlined. Now, the reason I'm plotting all of this on a time series compared to using a term structure is that the term structure only gives you a select pinpoint in time for when to look into the future regarding to the at-the-money prices. But that's not necessarily useful for historical analysis because it only shows one select pinpoint in time. Rather, let's say where I'm drawing up and down, like this, this would be more of the x-axis, and this would be the y-axis, and you would see these points and the values of the implied volatilities at those given points for its specific maturity. So it'd be like 7, 7, 30, 30, 60, 60, 90, 90, 180, 180 with the implied volatility curve. But it's not always that useful. Hence the reason there's a time series right here for you to analyze that on your own time. Next, similar to what we had before, very similar. All we have is the normalized implied volatility risk reversal over time for specific deltas. But the only difference on this one is that we have a subplot of the at the money that you're using as a divisor for that value. So whatever value enter into here, like let's say, well, for this instance is at the money 7, the at the money 7 will be on the subplot below where you have the risk reversal plots on the plot above. It's just an overall general comparison for you to use. Now, in addition to that, this one is also fairly similar, but rather, instead of looking at puts minus calls to get some analysis of skew, you can look at individual calls or put options in respect to implied volatility to use that as a denominator. Similar to what we had before, but the only difference as well is, well, the at the money. Now, this one is the exact same thing as 2 plots ago, but instead of having one at the money plot or subplot below, in this case it's the at the money 7, we are plotting all of the at the monies, but we're using one divisor in general. It's just to see how they compare overall amongst the trend of the risk reversal and the non-risk reversal. Now, similar to what I mentioned earlier when I was talking about term structure, I was using an example of specifically at the money implied volatilities. That is a general term structure that we will have accessible in our GitHub, but it won't be specific to this unique notebook. Rather, in this case, what will be unique to this notebook is a term structure that only looks at specific deltas. So in this case, it's implied volatility with respect to maturity on a specific delta basis. And of course, this is the limitation I mentioned earlier. You have to specify a specific date time in the past that is only one unique moment in time that you can see what the implied volatility is pricing for the given maturities in the future. And of course, you can do this on a live basis as well. But in regards to historical data, it's quite limiting when you want to look at a historical comparison. Hence the reason it's just good for an overall current market prediction. Now, in addition to that, we also have the term structure for individual deltas for specific option types here. Same as before, but the only difference is it plots all of the different deltas instead of just one, so you can get a more direct comparison. And that's the only difference here. Now, to make things a little bit more interesting, here we have the little melting phase that I mentioned previously at the top of the notebook. But in addition to this, this is a fixed strike implied volatility delta surface on a 3D basis where you can directly look at historical or live data and analyze how the surface is moving, whether implied volatility is shifting or not on different axes in regards to expiration and delta and so forth. But in regards to that, that is pretty much the gist of the entire notebook. I mean, there's many different components all together, which could be very useful for any type of analysis you may be looking for. So feel free to check it out in the GitHub, and that concludes today's video. Thank you.